In this assessment, we're asked to synthesize the ether shown using two different Williamson ether syntheses. Why are we able to make it in two different ways? Well, I've labeled that here. It's because both carbons of the ether are primary. Since the Williamson ether synthesis is an SN2 reaction with a strong nucleophile, having both sides be primary mean we can do it in either of two different ways. Let's look at one of them to get started. We can start by using the alkoxide here, and it could react with an alkyl halide like this. Now, if we think about the mechanism of the reaction, we can easily show it. Simply an SN2 reaction, a good nucleophile displacing a primary chloride. Now, how would we make this alkoxide? Probably it's going to be the sodium salt, and we could most easily make it by just reacting the alcohol with sodium metal. Again, make a strong nucleophile and have it do an SN2 reaction at the primary carbon. What's the other way we could do it? Well, we can simply flip the partners. Up here, we had this one as the alkoxide. Now let's have the other piece as the alkoxide. And so the alkoxide would look like this. And this alkoxide would want to do an SN2 reaction at this primary alkyl halide. Again, sketching our mechanism as such. Now, where would this alkoxide be synthesized from? Again, it's probably a sodium salt. Just to mix it up a little bit, instead of using sodium metal, we'll react it with sodium hydride, a strong base that would deprotonate this alcohol. Deprotonation of this alcohol would make this alkoxide, which once again can do the SN2 reactions. Two different ways to make the same ether using the Williamson ether synthesis.